Alright, so this is SEM 2 2010. I think this one that year a bit easier. But let's see. Let's see how it goes. Later I have to go off at just before 4, so I have to finish by then. I have to meeting to attend to. Okay, H6cm. Water. Air. Okay. Okay. So okay, so for this one, I guess this is SEM. Wait. What happened? This is SEM 1, SEM 2, 2010. This question very easy. This is 1, this is 2. For manometer, we say okay, can we say here and here same pressure, P naught. Okay, so here, here. Say this distance, say X, say. Alright, P naught minus P2 is equal to rho air, P naught, rho air, X plus H. P naught minus P1 is equal to rho water, oh that's a G, sorry, G, H plus rho air Gx. So P2 minus P1 is equal to this one. You take 1 minus 2. Alright, you'll get rho water minus rho air GH. Okay, that one's easy. From 1 to 2, use Bernoulli. 1 to 2. I think you're told here H is 6 cm. So you can work out rho water 998, rho air 1.23. You can work out P2 minus P1 equals how many kPa. Alright, and then Bernoulli from 1 to 2. I think P1 over rho G plus V1 squared over 2G plus H1 equals to P2 over rho G plus V2 squared over 2G plus H2. Now you can cancel out. V2 is 0, cancel out. So V1 is equal to P2 minus P1 on G on rho. This rho is air. I think 2 here. And square root. Alright. So you take that value that you found earlier and put in here, and then you can get meters per second. 6 cm, I guess, is 0.06 meters. That's a very easy question. Huh? And then, I think SEM 2 2010 had a different lecturer there. So the set question will be easier for you guys. Huh? This time won't be easy. Okay. One. Is that okay? It's pretty straightforward. That's the manometer pedostatic tube arrangement. Alright. The thing you need to do now is V2 is 0. The flow comes to a stop at the end of the opening of the tube. What's the answer? What's the answer? 30. Anyone got an answer? Huh? $30.9. Okay. Is that all you asked? What is the free stream flow speed? Yeah, 30.9. You all finish copying this one? Yeah. Okay. H. Okay. Find the expression of H. Okay. So in both sides, here, where's the pencil? Here, there is a force acting here. Alright? And there's a force acting here. Alright? After you convert the distributed force into a point force, you get picture look something like this. Okay? I call this F1, and I call this maybe y1, and I call this f2, and I call this y2. Alright. I guess we can assume the water here is free surface. Alright. So basically sum of the moments about the pin is equal to F1y1 minus F2y2, and that was equal to 0 when the gate starts, just begins to open or just begins to close or whatever it is. Alright. So F1 F1 is pressure at the centroid. Pressure at the centroid is this center of 1.5, 0.75. Rho G 0.75 pressure times area 1.5 times, I know what's the B, put that into the page. Alright, times y1. Oh. From here to here is 1 meter. So here becomes, here's what, 4 meters, is it? So 4 meters, 1 meter. This distance here would be 3.5 meters. Okay? That's the height of the centroid. The on that side is 1.5 meters. So the centroid height is 1.5 meters. Correct? So that's like the average pressure times the area. Average pressure, average at the center. That's just rho G HC. Alright? Is that okay so far? Alright, on the next one, area is 1.5 height times B into the page. Alright? And lever arm in this case, because we are starting from the top, alright, you can do the YCP. Huh? 3.25. Where is it 3.25? Yeah, but that's not the center. Yeah, that's the center of pressure. You need to do the YCP equals to, so this distance here, YCP, for those who don't believe, you can do Y bar plus IXX over AYC. Alright, so that is Y bar is 0.75 plus IXX is 1.5 cube times B over 12 divided by 1.5 times B times 0.75. Alright, that should come out to 1 meter. Okay? So if here is 1.5, here is how much? 1.5, here 2.5. Huh? What? Why is it 3.25? This is actually not the y1 is not the distance from the top to the center of the gate. It's the top to the center of pressure. Right? So the center of pressure is actually 1 meter from the surface plus 2.5, so it's 3.5. Is that okay? Huh? YC and YCP are not measured from the top of that line, but it's measured from the top of the surface. Okay or not? B is the depth into the page. It cancels out. Right here, it cancels out.
So we can do one, right?
Yeah, between one, so it doesn't matter. All right, minus F2 is rho G H on 2 H times B. This distance here is 4 minus 1, 3. 3 minus okay, same this distance here is 2/3 H. This distance here is 1/3 H. If you don't believe, you can always do this equation, you get that thing. And here, therefore this distance here is 3 minus 1/3 H. So the thing I always been telling you, pressure to calculate the magnitude of the force is the average pressure, the pressure at the centroid multiplied by the area, but that pressure acts at the center of pressure, and that's calculated through here, and these distances are from the hinge to the center of pressure. Okay, so if you were to do this one, I guess the rho and G can cancel out. B also can cancel out. So I'll get 0.75 times 1.5 times 3.5 minus H cube, no, 3H squared, 3H squared over 2 minus plus H cube over 6. Okay, a bit hard to solve, but can be solved if you. All right. I think I'm supposed to just leave it like that. Okay. Cubic means potentially you have 3 solutions. But some solutions may be negative. Or imaginary. Yes. Yes. H divided by 2 because that's where the center average pressure is. The average for triangle is in the center. But the center of moments for triangle is not in the center. Further down. Are there any questions or issues with that? What? Yeah. To calculate the magnitude of the force, you use the center of the centroid of the gate. The pressure at the centroid of the gate, to find where that pressure acts, so where that force acts, then you use the center of pressure. Yes, here, 1 meter from the depth, 1 meter plus 2.5 the time. Right? Yes, for moments you use YCP, where it acts, you use YCP, but for the calculating the magnitude, you use the YC. Okay? You happy with that? Not bad, 10 marks there. Okay. So here I presume it's atmospheric. So pressure equals to 0. Here and here, same pressure. Here, P1 equals to rho G H. What's the rho in this one? Water, 998. So equals to 998 times 9.81 times 20 cm. Is that okay? Then on this side, here you have pressure times area. So pressure, sum of the forces is equal to, well, this direction positive. Pressure times area minus F equals to 0. F equals to pressure times P1 times A. What is that, huh? What's the area of the cylinder, piston? Did they say? 10 cm. Is equal to 998 times 9.81 times 0.2 times area by 0.1 squared over 4. What's the answer? And the second part asks you, does it matter if you string the column on the right hand side? Yeah, no. Okay, what's the answer this one? Huh? 15 4 newtons. Is that right? All agree? Okay, part B asks you, if does it matter whether this cylinder on this side gets shrink by half or whatever? Does it matter? No, it doesn't matter. Okay, F equals same. Alright? Doesn't matter. So this F only depends on the pressure here, not on the pressure, not on the area here. Huh? Move out a bit. Okay, now happy? Right, next one. This is the only question with some challenge in the exam, in this exam. But otherwise was Okay? So in this case, as the water goes through a nozzle, a jet, water jet nozzle for steel cutting application. This is water for. So if you concentrate your jet to a very strong velocity, you can actually erode the steel. You can actually cut steel and plastics and other things. Alright? So in this case, the water flow comes in at a uniform velocity, comes out at with a parabolic profile. Yeah. R is the radius of the exit and R is the radius. Find the peak velocity, the force required to hold the nozzle, the force to hold the plate in place. Okay. Gravity can neglect the pressure. So the pressure at the entry is 15 atmospheres. 15 times 101, 325. Okay? Right? And the picture looks something like this. Right? Nozzle goes into comes out as a parabolic jet. Okay. Right. This. Okay. So it comes in here. Pen. 15 atmosphere. Here it's 1 atmosphere. Okay. Here 1 or 0? The nozzle is at high pressure, but it keeps the 15 atmosphere. Is that 15 atmosphere gauge or absolute? Normally it's gauge. Alright. So it's, if you can either do 15 and 0 or 16 and 1. Alright. Normally it measures. This question didn't say, so I would have to accept both. Oh, not take one. But the question didn't say. You want put here 1, then that's okay. Put here 1. Here 1. Okay. Alright. I think I accepted both because the question didn't say. Although the diagram says. Alright. So if you want to put 15 and 1, alright, it's easier then to put it 14 and 0. Okay? It's easier that way. If you put 15 and 1, then you have to worry about the pressure on the outside and so on. Okay? Alright, so then this is our control volume. Okay, so m dot in equals to m dot out. Alright. So using this one, I should be able to find that Umax that they are talking about. M dot is rho. What's this area here? 1 cm, 1 meter. 1 cm. Rho area is pi 0.1 cm, is it? O1 squared over 4. Velocity is what? 0.4 equals this one 1 mm. Oh. Okay. Rho. Okay, that one is constant. This one need to use velocity dA. Okay. I think rho can cancel out. Velocity dA. What is velocity dA? Velocity is Umax Umax 1 minus r squared over r squared. 1 minus r squared over r squared. dA is 2 pi r dr, isn't it? Okay, that dA is 2 pi r dr integral. R goes from 0 to 0 0.0011 mm, is it? 05. Half an mm. Because that's the radius. Alright? Diameter 1 mm, so it goes to half an mm. Alright? Because the radius. Right? 2 pi r dr, that's fine. Okay? You're okay with that? dA is 2 pi r dr? Alright? I talked about that many times. dA, one area can be broken down into one strip, and that strip thickness is dr, and the length is 2 pi r. Right? So that's 1 dA, 1 unit of dA. You integrate from all the way to 0, all the way to out. Okay? So this is a circle, this is the dr. This is dA is equal to 2 pi r dr. This distance is r. This distance is dr. Is that okay? So that one equals to pi 0.01 squared over 4. Actually, you can tidy a few things up. This pi can cancel out. 4 and 2, 8. Okay. Umax. R, you get r minus r squared on r minus r cubed on r squared integral dr is equal to this one go here 0.01 squared over 8. Huh? Oh, sorry, 0.4. 0.4. 0.4. Okay? And then Umax. Oh yeah, there should be 3 here. Come r squared over 2. Hey, no 3 here. Haven't ever integrated. Now integrate that. R to the 4 over 4 r squared 0.005 0 equals, what is this thing? Okay, so Umax R is 0.0005 squared over 2 minus 0.0005 to the 4 over 4 0.0005 squared. Okay, this one actually can cancel out. Is equal to what's this answer here? So Umax is equal to equals to this one is 0.0005 what's the answer here? Anyone calculate? Huh? 3? This one 0.01 squared times 4. Huh? Huh? This one. And Umax? Umax? 80. Okay? Huh? What? Question 2, what? Question 2 got 3H. What we got 3H values? Ah? Ah. Yeah, you could potentially have 3 solutions, potentially, but some solutions could be imaginary, some solutions could be negative. They didn't ask you to find the answer, they asked you just to come with the expression. But if you find the answer, it's, I guess your calculator can do it, isn't it? Yeah. You can solve the equation, but you know, if you can't answer, it's up to you. Again, as I said, some solution could be imaginary, some solution could be complex, some solution could be negative. So I think there's only one real solution for that one. 2 real solution. Possibly 2 real solution? Yeah, you can balance at 2 points. And the solution, the H must be less than the height of the hinge. H must be less than, if not, it's not a valid solution. Okay. I mean, come on, H cannot be more than 3 meters, not? Huh? Yeah. The valid solution must only between 0 and 3. Is it okay so far? Can I proceed? Any questions? Alright. No, then I proceed. Sum of forces in the X is equal to M dot out V out minus M dot in V in. Okay? That's the standard. Sum of forces, I think this one is P1 A1 minus P2 A2. So this one 0. Alright? Plus F external equals to M dot out V out is the more complicated one. That's M dot out V out minus M dot in V in is what? Rho rho A in V in multiplied by V in. Okay, so this one is 14. 14 times 101,325. 14 atmospheres times area is 1 cm, is it? 1 cm, 1 cm. Pi 0.01 squared over 4 plus F external equals to 998. Area is pi 0.01 squared over 4. V in is what? 0.4 meters per second squared. Okay? You all agreeable with this one? So this one I'll do separately, then we put back in here. Because that one we need to integrate. Okay. So this is the easy part. The hard part is M dot out V out is equal to, well, I'll put inverted commas, integral of rho AV rho V times V dA. Alright? Rho V times dA, that's your M dot. and then times your mass flow rate times velocity. Alright? Basically, this integral, because not every piece of fluid leaves at the same velocity, and because it leaves at different velocities, it carries with it also different amount of momentum. And this one captures that. Slow moving fluid carries out less momentum with it. Fast moving fluid captures out more momentum. So in this case is rho 998. That one constant can walk outside. V squared is U max squared 1 minus R squared over R squared squared. dA is 2 pi R dr. Integral from 0 to 0.0005. Alright, that's velocity squared. Is that okay? I think only one or two years from it. But this year, I think if the question comes out, I expect you within the tutorial problem, within the quiz, remember? If you integrate, okay, so that one no problem. Equals to 998. This one is 80 squared. This one is what? Integral 0.0005. What is this? 1 comes 1 squared, that's fine. Minus 2 r to the 4 over r. Minus 2r squared over r squared. Plus r to the 4 over r to the 4. Alright, multiply by 2 pi r dr. Okay? So this is actually 998, 80 squared. This one is 2 pi, also can walk outside. R integral 0 to 0.0005 r minus 2r cubed over r squared plus r to the 5 over r to the 4 dr. Alright, is equal to 998, 80 squared, 2 pi. This one becomes r squared over 2 minus 2. This one 4, so comes r to the 4 over 2r squared plus r to the 6 over r to the 4 dr. No more dr, sorry. Close bracket 0.0005 0. Huh? Oh yeah, sorry. 6. Okay. Half minus half 0 plus 6. So the answer here should be 998, 80 squared, 2 pi. What's the answer here? Answer here should be 0.0005 squared on 6. Okay, if you put in, alright, because small r and big r is the same value now. Alright, after integration, small r and big r is the same value. So this one, half minus half, 4. So 6. R to the 6 divided by r to the big r to the 4. Both small r and big r is the same value. Okay? So finally, you put this number into here. Alright, you put this number that we found into here. Alright, and then we can find what the F external is. Okay? What's the answer? Right, I'll let you work out that one. Okay, this was actually in the x direction. Alright, this is actually, yeah, in the x direction. So x direction is that way. What's the y direction? I think all 0, isn't it? Okay, in this case, fy equals to 0, f external comma x equals to what? Anyone managed to work out what the answer is? Huh? The final answer, this one, put inside here. Yeah. Oh, what is this one, you said? 1.67. Huh? What the force are? F external, I don't know. 1.55 newtons. What's the answer? Negative 108. 109. Minus 109.75. All agree? Okay. Then the next part, I think ask you the force required to hold this plate in place. Okay. So part 2, plate in place, plate. Sum of the forces in the x equals F pressure. This time, this case, this one is 0 plus F gravity. Okay, that one also 0 plus F viscous. That one 0 plus F. What is that one? F on external equals to m dot out v out minus m dot in v in. Okay, this one is 0 because it's not leaving in the, there's no x component in the stuff that's coming out. Okay, because v out comma x is 0. M dot in v in, well, we could do this whole integration again, but it will give you the same number. Okay, if this is correct, 1.67. Alright, so then it's just 1.67 Newton. Okay. F external comma x. Alright, I think Fy also 0 . So nothing really happening in the y. Alright. Right? If you didn't catch what I just said, these two are the same. M dot out, V out leaving the jet is the same M dot in hitting the plane. You assume that the flow, the velocity doesn't change, the speed doesn't slow down or anything like that. Okay? So whatever leaves the jet, M dot V out must enter this one. You can do the same integration again, by all means. Right? You get the same. Because for part 2, if you see out here, it's no longer inside a pipe or nozzle. I think it's all atmospheric. Okay? It's like your pipe, your impact jet experiment already. Okay. Huh? So all atmospheric. Means the F external, this is the force required to, this is the force placed on fluid. Okay? So if you hit your jet, it's going this way, your plate on fluid is going this way. Right? This one is external, means external plate on the control volume of plate on the fluid. Right? What did the question ask? Force required to hold the plate in place. Nozzle in place. Force. This one is F. Hold the plate in place. Hold the. Yeah, that's correct. It's fine. Yeah, this is fine. Force. So this is the force required to hold the nozzle the plate in place. The earlier one is the force required to hold the nozzle in place. Right? Because that's the fluid on the nozzle on fluid. So it's that force you need to provide nozzle on fluid to hold the nozzle in place. Huh? Yeah, y is 0. For the plate, also 0. Because it's just like your impact jet, half goes here, half goes here. They'll can. Okay. Now we're doing this one, question 4. Okay, so I think they said the length of pipe as a palm. The length of pipe is 400 meters. Alright, this is 0.1, this is 0.2. Okay, what else did they say? 2 elbows, 0.29. So KL is 0.29, KL is 0.29. Roughness 0.015. This seawater rho is 1025 kilogram per meter cube. 1.88. mu is 1.88 by 10 to the minus 3. Alright. What other losses are there? Valve, 2 elbows, an entry, an exit. So KL here 0.5. So here KL, they didn't tell you, so you assume 1. Open valve KL 0.11. Anything else? Diameter is 114.3 mm. Okay. What about the flow rate again? Huh? So flow rate 0.03. Right, you find H pump. Is that okay? So velocity in the pipe is Q over A is 0.03 over area is pi 0.1143 squared over 4. Alright, that's your first step. After that, you work out your Reynolds number, rho VD over mu, and your relative roughness is 0.015 over 114.3. Yeah? Yeah. In fact, all the time it should be 1. Sometimes they tell you, sometimes they don't. Then lose marks. No, I think 1 or 2 marks more. Okay, what's the velocity? And what's the Reynolds number? And then we look up F. And then after that, we put in the energy equation. Reynolds number is 1.8 million. Relative roughness 0.00. Huh? Relative roughness comes to 1.6. 0.01. What's the velocity? The 100 meter height later, that's H2 minus H1. Right? It's nothing to do with the piping system. It's to do with the inlet and exit. Right? You take there 1 and then 2. H2 minus H1. Some people in the water up to right? And the power 5. 1.8 times the power 5. Is that okay? Everybody happy with that? Okay? You happy with that? Then we look up our Moody chart. Where's our Moody chart? Mau dicat sama 1.8 by 10 to the 5. It's about here, 1.5, say about here. Roughness is what? About here lah. .0.017. Huh? Is that okay? The power 5 or power 6? Power 5 is there. Is that okay? So 1 or 2. Oh, well. Maybe a bit more than that lah. Maybe 1.7. 1.3 or something like that. 173? Is that okay? Yeah. Alright? All agreeable? Okay. Okay. F is what, huh? 0.0173. That's fine. That's good. Supply energy. One to 2. P1 on rho G plus P1 squared on 2G plus H1 plus H pump is equal to P2 on rho G plus V2 squared on 2G plus H2 plus what else? Head loss. Head loss is F, L on D plus sum of KL V squared on 2G plus head turbine, in this case don't have. Okay, I think pressure also don't have because they both are same pressure or atmospheric. This one also don't have. Alright. Oh yeah, there's a square there. The V1 and V2 don't have because we're starting from a big tank, or starting from inside the sea and getting up to some reservoir up there. So H pump is equal to H2 minus H1 plus F L on D plus sum of KL V squared on 2G. Okay, and that's how many meters. Okay, this one I think it's 100 meters. This one I don't know. Right, but I guess you can plug in all numbers. Remember to add up all the losses, all the minor losses, 0.5, 0.29, 0.11, 0.29. Right? L I think is 400 meters, isn't it? Right? L is 400 meters. Diameter is 0.1143 and so on. Huh? This velocity is the velocity in the pipe. Yeah, not V1, V2 in the big reservoir. No, this generally use the velocity in the pipe. It could be V1, could be V2, could be any, but it needs to be the velocity in the pipe. which is not the same as the starting and end velocity. You can start at one velocity, end at another velocity, but velocity effect will be different. There could be two sections of pipe, right, pipes in series and so on, so they get different velocities. Huh? 127.3. All agreeable? You repeat again? The velocity? 0.00013, yeah. Triple O. Right, I lost one O. Triple O. Huh? Yeah, so if triple O1, we follow this line, you use this graph. And wait. And where our Reynolds number meets that line, then that's our F. Right? Okay, what happens if the seawater, if the tide goes out and H 2 minus H1 is 100 plus 2.5 meters. Is that what it's asking? Alright. How much more head needs to be supplied when the tide goes out, leading to a fall in sea level of 2.5 meters? What's the answer? 2.5. Okay. Alright. How much more? 2.5? Yeah? Huh? If the tide goes out, this level same, this level drop by 2.5. How much head is required? How much more head is required? About 2.5 more. We assume that the length of pipe doesn't change because the pipe all starts deep inside the water. Anyway, okay. So the 2.5, you just need, right? No other parameter changes. Okay. Is that okay? Yeah.
So either we get the 3 marks or we don't get the marks.
Yeah. No, I just don't. But... Yeah. Okay. And do question 5a. This here also not bad, huh? Let you choose also. Or the 4 questions, choose 3. Okay, let's try. Not bad. 5a. Power is a function of Newtonian fluid, so mu L mu rho omega L omega as shown in the figure. H as shown in the figure. Okay, is that it? Alright. So you need to choose. I will tend to choose rho, L, and omega. Right? Because I told you choose rho, the length, and the velocity. In this case, there's no velocity, but there's a angular velocity. That's also dependent. Alright? You choose rho, L, and omega. You could choose the diameter, right? Rho. That's the diameter, is it? Okay, no problem. Alright? Huh? Is it weight of blade stirrer also got? With the blade stirrer of length L and with W. Okay. Okay. Power. What's the units of power? Force times velocity. Force times velocity. Force has a dimensions of m, mass times acceleration, L on t squared times L on t. So power has the dimensions of m, L squared over t cubed. Alright, that's fine. What's this one, huh? ml over t, dimensions of viscosity, shear stress is equal m over lt squared, m over lt. Alright, but if you don't know, that's shear stress equals to mu du on dy. Shear stress is force per unit area. Okay. Force is what? ml over t squared divided by L squared is equal to the dimensions of mu L over t over L. So dimension of mu is m. This one will cancel out this one. This one will cancel out this one. M over LP. Okay, this one is mass m over L cube. This one length. This one length. This one is omega. Omega 1 over t. Okay. Right. So, usual suspects, you choose 1, 2, 3, 4, 5, 6, 7, 8. Got 8 variables. You have 3 basic dimensions. So 8 minus 3, you get 5 groups. Okay. Normally, there's a rule which 3 you choose. They must contain all the basic dimensions, and they cannot form the dimensions group on their own. So normally, if you choose mu, rho, and rho, L, and one length, you can choose L, H, D, or W, whichever one you choose. But I'll just choose L, rho, L, and omega, the repeating. rho, L, and omega. So on this side, I'll have P to the power of rho to the A, L to the B, omega to the C equals to dimensionless. Right, power is what? M over L squared. M L squared over T cube over rho M over L cube. L is just L to the A to the B, omega 1 over T to the C. Okay, so that's equal to M to the power of 1 minus A, L to the power of 2 plus 3A minus B, and T to the power of 3 minus 3 plus C. Is that okay? So A equals to 1, C equals to 3, therefore B, therefore 2 plus 3A plus 3 minus B equals to 0, B equals to 5. So this one becomes P over rho to the rho, L to the 5, omega to the 3. Okay. The other one that we need to do is rho to the A, B, C, D, L, E, rho, L, I didn't know this answer. You know this answer? No? Rho omega square L over mu. It's a Palm Reynolds number. Okay? If you don't believe, you can by all means do. And then the rest all know also actually. Yeah, if you're confident, go for it. H over L, D over L, W over L. The other ones will be D over L, H over L, W over L. So that's your 5 already. So P over rho L to the 5 omega cube is equal to, is a function of rho omega square L over mu, D over L, H over L, W over L. 1, 2, 3, 4, 5. Okay, done. Okay? This one also is your pump power coefficient, isn't it? It's in your formula sheet. Power divided by rho, the diameter of some length scale to the 5, omega to the 3. So if you're smart, you can see, hang on. You see, hang on. This number here looks pretty familiar. Eh? So we get that one actually. You can choose anyone. But you must follow those rules. Yeah, but yeah. Here normal choice, you cannot choose more than one of the next. So you can either choose D, H, omega, or W, but not more than 2 of them. So it's your choice either rho, omega, L, or rho, mu, L, rho, omega enough. Like, make your life more complicated. You, other way around also can. No problem. Alright, are you all happy? Okay, I haven't finished shopping yet. Okay, all good? This is not the only answer. You can have more than multiple answers. As long as you did the procedure correct, that's fine. Alright? Huh? In your exam, if you're confident, this one actually you can get from the palm. Confident. If you write the answer, then I'll give full marks again. I don't know where. Alright? But then if you get it wrong, then I have no way to give you. So what to know to figure out to give you intermediate. Huh? Huh? Yeah. Oh, sorry, this one wrong, huh? Sorry, this should be square here. Yeah, inverted all also still okay. Huh? It's the same. 1 mean 2 over 1, 1 over 2. What mean different answer? If you do it the other way, you get mu over rho omega L squared. Yeah, that's correct. This is a dimensionless group. This is also a dimensionless group. You use either one, is okay. Alright? Just like here, alright, L over W or W over L, also okay. Alright? Both also deserve full marks. Huh? Can you finish what? 4 o'clock. I think can. We only got a few bits to do. Alright. No, the last one actually you're not doing. The question 6 we are not the alright, let's do question 5B. Alright, now this. Let's continue. Right. And go along a flat plate of P1 meter per second from a boundary layer. The transition from a laminar curve occurs at REX 500,000. At what distance does this transition occur? Okay, that's pretty okay. So REX is rho Vx over mu. Is air is equal to 1.23. V is what? 1. 1, yes. Yes, 1. X you want to find over mu. Mu is what? 1.8 by 10 to the minus 5 meter square per second. Oh, no, Newton seconds per meter square. Okay? And this is equal to 500,000. So x equal to 5 marks, not bad. Alright, transition occurs at that location. What else? Huh? What's x? Huh? 7.3 meters. Okay? So, because at such low velocities, the transition to turbulence happens very far downstream. Okay. Second one, they tell you now x, the plate cut shorter to 20 cm only. Alright, equals 0.2 meters. Alright, ask you calculate. The drag per unit width. So the width into the page 1 meter. Alright. So calculate F drag. F drag is equal to CD times half rho d squared A. Alright. What is CD? 1.328. 1.328 over square root of REL. R is rho V L. L is 20 cm, 0.2 over mu times half rho V square A. A is 0.2 times 1. Alright? Okay? That's the answer. That's another 5 marks. Okay, in this case, V is still 1, rho is 1.23, V is still 1.0, rho is 1.23, mu is 1.8 by 10 to the minus 5. Right? Is that alright? Okay. Huh? Not likely. You can pray. Huh? I doubt it. Okay. Alright, this one. You all done with the earlier one? Any questions? Okay, so this one is basically Q as a function of, no, wrong. Head as a function of Q. So it does something like this. This the shut off head here is 22 meters, and somewhere here, where's best efficiency point, where the efficiency is maximum, it's somewhere here. Hello? Yeah. Not really, right? I'm in my studio at the moment. I can get there maybe about half an hour. Okay? Okay? Okay. Okay, sorry about that. That's how I finish this off. Here is what? 18.3. Here is 0.029 meter cube per second. Okay? So for part A, they just worry about shut off head, H2. Alright? So case 1, the shut off head, H0 is 22 meter. Case 2, H0, 2 is, we don't know lah. That's what we want to find. Omega 1 is 1160. Omega 2 is 1750. H0 omega. What's the next one? Oh, diameter. Same, isn't it? D1 equals to D2. Is that right? Flow rate on, don't touch first. Let's do part A first. H0, yes, T1, 30 cm. A centrifugal pump with an impeller of 30 cm. Okay? So, what's happening here? Omega D. Okay, so what is CH? Alright. There's someone know GH over omega squared D squared. Is that right? So that for 1 equals to GH over omega squared D squared for 2. Alright, so what is H naught 2? What is that? 50 point. Is that agreeable to everybody? Okay. For case 2, head and flow rate. So case 2, H1 is 18.3, Q1 is, what is that? 0.029 meter cube per second. HQ, what else is there? Let's see that. Alright. Omega 1 is 1160. Omega 2 is 1750. We want to find H2, question mark, and Q2. Alright, H2 find the same way. HQ, what is Q? CQ equals to Q over, what's omega D cube? Omega D cube. Alright, so this for 1 equals to for 2. Okay, so you can calculate that. So same, D1 equals to D2. What's Q2? Q2 is just 0.029 times 1750 divided by 116. So what is that? 0.044 meter cube per second. H2? It's the ratio of the square of the omega. Huh? 41. 41 only. Meters. Okay? Still copying ah? What? H2 same ah? It's the same relationship, but this is a different operating point. This is at the best efficiency point. This is at the cutoff rate. Cutoff rate basically this is at Q0. This is what happens. This one is at 41. I think it should be 18.3 times 1750 squared divided by 1160 squared. Is that right? Any other questions? You all okay? You can get it? Okay, so here you must know K prime is 2, N prime is 0.5. Okay or not? Alright, from there. After that, the standard straightforward way to do it. Okay. Tell you density rho, U, length, diameter. Okay, generalized Reynolds number. I think mu AP is equal to 8 K prime 8U over DI to the N prime over 8U over DI. Alright, that is what? RE prime is equal to rho U DI on mu AP equals to what? Alright? That's the standard procedure we always follow. We always do. Alright? Fning K prime and prime get from here. 2 times this one to the power half. Alright? Fning equals to 16 on RE prime if RE prime less than 2200. I have a feeling this question is less than that, but I didn't see any chart. I have a strong feeling. Okay, and then if that is the case, pressure drop, shear stress on the wall over half rho P squared is equal to F fanning. Therefore, shear stress on the wall equals to what? Shear stress on the wall equals to delta P on L D on 4. Therefore, delta P equals to what? Okay? K prime and N prime come from the 2 square root A over D. Right? You need to. That's the only part that may be slightly challenging. You need to get that one. Then the other one is just crank the handle. I told you how to crank the handle like this. What's the new AP? 0.204. Is that right? RE prime? Huh? 646? Huh? 646.7. Okay. Then, therefore, F fanning is 16 over 646.7. What's it get? 0. Oh. Oh. There must be a typo here. Huh? What is it? What is it? What's the F fanning? For fanning or that F fanning is 0.0? 0.02. Okay. Shear stress on wall. Hello? Not so soon. I have a meeting after this. Maybe after 5. Shear stress 19 point. 3,900 point. Okay. Yeah, big yeah. All right. So I think that's the end. Question 6. I think I did this with you guys, isn't it? Yeah, I did this with you guys. The mechanical one. Okay. Question 7. This one is using a different type of method to predict the pressure drop, so it's not relevant. Right? Not relevant this semester. Okay. So that's it. Okay. All the best for exams. Normally no.